All right, so third lesson in a row looking at trigonometric values beyond acute angles. And this really, there's two distinct parts of this. One looking at, well, returning to the sine law, but what we call the ambiguous case, and the second part is to introduce a few identities. So these two halves of this lesson are fairly different from one another, but all involve trigonometry. And so first, the ambiguous case of the sine law is when sometimes you may not realize we can solve a problem, make no algebraic mistakes, but get an answer that can't be correct. And for example, if I look at this, I want to find the value of b, or the angle theta right there. And if I use the sine law, which is a great way to set this up, I can say the sine of a, which in this case is 38 degrees, divided by the side opposite from it, 10.7, must equal the sine of b, or theta, but I'll just go with b, divided by 16.3. All right, so I can solve this by cross multiplying. Pretty quickly, I get to the sine of b equaling approximately 0.93787, and goes on and on and on. That's it. I use the inverse sine of b, making sure I'm in degree mode, and I get the angle of b being approximately 69.7 degrees. All right, so now if I just look at my diagram, that can't be correct. Now I can't assume this is drawn to scale, but that is, this angle B is definitely an obtuse angle, and I have here an acute angle. So this can't be correct. It's not meaningless, this roughly 70 degrees, but it's definitely not the angle. So what is it? Well, what I have inadvertently figured out is not the angle I'm trying to find. I figured out an angle that looks more like this, where I imagine this side, CB, being kind of swung from here to here. And if I look at this triangle, this larger triangle now, that's 69.7 degrees. That's that angle right there. And it's not meaningless, but it's not the angle I want. I want this angle right here. So how can I figure it out? Well, it's quite quick. Because I mentioned we kind of can visualize this line here, this side here being swung over here, which means those two sides are the same length. They're both 10.7, which means these two angles here must be the same length. They must both be 69.7 degrees, which means if I want to find angle theta, all I need to do is take 180 and subtract that 69.7. That'll be the difference. And so this all goes back to the last lesson where we saw in the first quadrant, all your values of sine are the exact same in the second quadrant if they have that same reference angle. And this is really a consequence of that. And so that said, all I need to do now is realize, okay, that angle is not 69.7 degrees. It's going to be 180 minus that. And so let's finish this off and say, therefore, theta is going to be the same as 180 degrees minus what I just found. I'll say minus b. Or in this case, approximately 180 minus 69.7 degrees, which is approximately 110.3, or I'll leave it to three significant figures, 110 degrees. And that there makes much more sense. Now, in this case, I had a diagram. In the second case, I don't have a diagram. I had to say I have triangle ABC. A equals 40 degrees. Side A is 15 units. Side B is 20. Now, I can set this up any way I want. I should get the same answer. I make it much simpler if I set up my triangle in a similar fashion to what I see up here, or to what I see up here. So I'm going to be very boring and consistent, in which I want to set up a triangle that has, a horizontal base. Side A is right here. Angle A is 40 degrees. Make that side a little bit nicer. I'm going to call this point B here, and I'll call this C up here. And I'll draw a triangle like this. Keeping in mind, it's not drawn to scale, and I may have to, adjust some aspects of it. So I have 40 degrees there, which means side A is 15 units right here. Angle B, I don't know. That's what we're trying to figure out. But side B is 20. And so just keep in mind, right now, I can see that 15 is less than 20, which means there will be a second possibility here, just like I could see in this question. This 10.7 was less than 16.3. So for a question set up like this, there's always going to be two possibilities. if we didn't have the diagram drawn already. Now keep in mind, in this first question, the diagram was drawn, so it's very specific what angle we're trying to find. In this case, there was no diagram drawn, so there will be two possibilities. First, let me stick with this. Let me find angle B. Same idea as before. The sine of A, or in this case 40 degrees, divided by the side opposite from it must equal the sine of B divided by the side opposite from it, 20. And so cross multiply pretty quickly, I get to three significant figures. I get B equals approximately 59.0 degrees. All right, so that angle there is that angle right there. That's the 59 degrees. However, there's another possibility in which I imagine that side of 15, imagine it being swung over here and having something like this as well. Oh, maybe I should make that a little bit more accurate. I'll swing it more like this, because really these two should be the same. So I don't know, something like that. So imagine that side here. And so I have another B. I'll call this other B, B prime, put a little apostrophe there. And let's try to find this angle right here, which again, keep in mind, should be quite quick because I know that this angle here is also 59 degrees, which means this angle of B prime, the other B, must be 180 minus 59. And so that's my other answer. So I have this, and, or whatever you want to say, my other B, I'll call it B prime, must be the same as 180 degrees minus what I had before, or in this case, approximately 180 minus 59.0, which is approximately 121 degrees. And those are my two possible values for angle B in this scenario. All right, so with that said, that's kind of the first half of this. The second half is distinctly different, looking at identities. And maybe before I go to here, there's two key identities we want to work with. One of which we saw in the last lesson, this quotient identity for tangent. The tangent is always equal to sine over cosine. And if you see this sort of, perhaps looks like a typo, this triple equal sign, that's not a typo. It's a symbol we sometimes use for identities to state that this is an identity, which means the left side always equals the right side. It's always true. It's essentially an equation, though. And there's another identity, this Pythagorean identity, in which sine of an angle squared plus cos of that same angle squared must always equal 1. And as we saw last day, this notation of sine theta squared is more commonly written like this, sine squared theta, but they mean the same thing. So with that said, these last couple questions are about working with these and understanding them and really just being introduced to these identities. There's a lot of trigonometric identities. There's an infinite number of trigonometric identities. These two are some of the more important ones that we end up seeing a lot. And so I know the sine of alpha is 1/3. I want to know the exact possible values for the cosine of alpha. So as we saw already, sine and cosine can be related with that Pythagorean identity, and I'll write it like this. I'll say the sine of, I'll go with alpha squared plus the cosine of alpha squared. That must always equal 1. All right? And keep in mind, the sine of alpha we know is 1/3. So this part here must be the same as 1/3 times 1/3, or 1/3 squared. So I'll write that as 1/3 squared plus the cosine of alpha squared must equal 1. That's not a highlighter. There we go. All right, hopefully we can now realize, okay, if we're trying to solve for cosine of alpha, well, we want to isolate that. It shouldn't take us too long. First, 1/3 squared is 1/9. And let me subtract that from both sides. I pretty quickly get to cos squared of alpha equaling 1 minus 1/9, which is 8/9. And remember, the cosine squared alpha, it really means cosine of alpha all squared. So I want to square root both sides. And so I get to the cosine of alpha, which is what I'm trying to figure out, as plus or minus the square root of 8/9. Now I want to clean this up a little bit, but please remember again, every time we solve something like this, every time we have something squared equaling a positive number over here, there's always two possibilities, the positive solution or the negative solution. And then while I'm effectively done, I just want to simplify my answer. I don't want to decimalize it. that 8 in the numerator is not a perfect square. So if I decimalize this, it's no longer exact. I want to keep this exact. So a few things I can do. 9 is a perfect square, so I can easily write this as plus or minus just root 8 over the square root of 9, which is 3. That's a little bit nicer. And while root 8 is not a perfect square, there is a perfect square of 4 I can factor out of it. If I factor out that perfect square of 4, I get plus or minus 2 whole, the square root of 4 times root 2 over 3. And that last example is considered to be the simplest. But I didn't ask for it to be in simplest form, so this is just as good. Technically, this is just as good as well. I didn't ask for it to be in simplest form. But since that 9 is a perfect square, it makes sense to, evaluate it. All right. This last question can be done in a lot of different ways. In fact, some other ways are actually far faster, but I want to focus on using identities here. And so I have the tangent of beta equals negative 3/4, but I'm telling you that beta is between 3 pi over 2 and 2 pi. And we want to find, okay, what's the value of sine of beta? It's a pretty abstract question. First, let's realize what this restriction here means. Beta is between 3 pi over 2 and 2 pi. So let's think about an angle in standard position and realize what that's describing. That's describing an angle between 3 pi over 2, which is right here, and 2 pi. So it's describing something in this quadrant right here. Whatever angle beta is, it's something in this quadrant. I'll just draw a terminal arm in this quadrant. I don't know, something like that. So we're looking at an angle that's something like that, somewhere in that quadrant, okay? And the reason that matters is we're trying to find the sine of this angle. And if we think about our CAS rule, I can see right away that only cosine is positive in that quadrant. So I know my answer is going to be negative. I know my answer for the sine of beta will be less than 0. Okay, with that said, how do I actually figure out what the sine of beta is? Well, I want to use those two identities that we've seen and kind of put them together. So for example, that first identity, that tangent of anything, in this case, beta is always the same as the sine of that same angle divided by the cosine of that same angle. This is always true, which means we can isolate sine or cosine any way we want. Keep in mind, we know the tangent of beta is negative 3/4. So I'm going to rewrite this as negative 3/4. Negative 3/4 equals sine of beta over cosine beta. All right, what do I do with that? Well, let's leave it for a moment. There's also the other identity in which we know the sine squared, I'll go with beta, plus cosine squared beta must always equal 1. And notice we're trying to find the sine of beta, which means I can see right here that if I can take this cosine of beta right here and use this equation to substitute it with something in terms of sine, I can solve that equation. I can solve this equation here once I have just the sine function. And so what I want to do is pause this equation of sine squared beta plus cos squared beta. Look at the equation over here involving tangent, or in this case equaling negative 3/4, and I want to isolate it to be just in terms of sine. I want to isolate sine because then I can substitute that to the other equation. And it's pretty nice to substitute sine. If I want to isolate sine, I could multiply both sides by cos beta, for example. And if I multiply both sides by cos beta, I get the sine of beta equals, I feel like I just did something wrong here. Actually, sorry, I am. While I can't isolate sine, I want to isolate cosine so that I have just, so I can substitute cosine with this. So my apologies. I want to isolate cosine. And if I isolate cosine, I can pretty quickly get to this. The cosine equals the sine of beta over negative 3/4, which is needlessly messy. And so let me, instead of showing sine of beta being divided by negative 3/4, let me instead show it as being multiplied by negative 4/3. So negative 4/3 times the sine of beta must equal the cosine of beta. And now that I've isolated that, I can take that negative 4/3 sine beta and substitute it right there. But I got to square it all. So I get now, right here, I still get my sine squared beta plus, instead of cos squared, I have negative 4/3 sine beta all squared equals 1. Make that beta look more like a beta and less like a b. All right. And now, as messy as this looks, things are going to come together quite nicely now, because that equation I just wrote down only has the sine function, which means I should be able to isolate sine beta quite quickly. And so first, let me erase some of this highlighting here, and I get sine squared beta plus, let me square what we have inside here. Negative 4/3 squared is positive 16/9. That's nice. They're both perfect squares. How convenient. And sine b times itself is, sine beta times itself is sine squared beta equals 1. Now these two terms here are like terms. I have 1 sine squared beta plus 16/9. Put them together, find your common denominator, add them up, and you get 25/9 of these sine squared betas, and that all equals 1. And I'm just about done. Solve for sine squared beta. Well, I would first divide both sides by 25/9, which is the same as multiplying both sides by 9/25. However you look at it, I get sine squared beta equals 9/25. I want to square root both sides. That means I get the sine of beta equals, don't forget the plus or minus. Remember, anytime something squared equals a positive number, you have two possibilities. In this case, the square root of both 9 and 25 are perfect squares, so I get plus or minus 3/5. And all that's left, because right now I have two possibilities, but remember a long, long time ago, I realized that my answer must be a negative number because we're looking in this fourth quadrant, and cosine is the only positive function in that quadrant, which means I now know my answer. I can say, therefore, that's a weird looking sign. Therefore, the sine of beta must equal just the negative 3/5. Phew. Now that's it. There's definitely other approaches, but the focus of this was to use these identities and look at how these identities can connect these various trigonometric functions together. And there's a lot more that we could learn about identities. For this course, though, we don't need to be aware with about too many of them.